Namaste students. Today we will study transistor characteristics, and also I will teach you how to perform this experiment. The aim of the experiment is to draw the input and output characteristics of an NPN transistor in C configuration and to determine its current gain and input resistance. Now let's understand fundamentals about this transistor characteristics, then we'll go ahead with the experiment performance. So what is a transistor? So transistor basically it is three terminal device. So basically you take a PN junction and take another PN junction, you sandwich. So it will be like this. Okay. So this is PN junction, another one is PN junction. So you sandwich, so it forms two junctions. Okay. Therefore, this will be one terminal, and this will be another terminal, and this will be another terminal. So basically, transistor is three terminal device. So which contains, so this is the base, emitter, and collector. Okay. So it is a three terminal device. So we call it as a transistor. So what are the applications of transistor? So these transistors are actually used in switches and also used as amplifiers. So these are the applications. Okay. Now what are types of transistors? So basically there are two types of transistor. One is NPN transistor, second one is PNP transistor. The one which you are seeing here, this is called as NPN transistor because we are taking PN junction and sandwich, so it forms a NPN transistor. It means P-type semiconductor is sandwiched between two N-type semiconductors, it forms NPN transistor. So similarly, if it is PNP transistor, take a N-type semiconductor material and sandwich between two P-type. So this is called as PNP transistor. Okay. Now what are the modes in which these transistors can be used? So we have some three modes. One is CE mode, second one is CB mode, third one is CC mode. What is CE? This is called common emitter mode, this is common base, and this is common collector mode. So in this common emitter mode, okay, so emitter is connected commonly to the base and collector, so that is why it is called as common emitter mode. Now let's come back to the circuit. So there you will understand how this common emitter mode actually looks like. Now what are the circuit symbols? So if it is NPN transistor, so NPN transistor can be represented like this. Okay. Now this region is called as base, and this terminal is called as emitter, and this we call as collector. So this is true for NPN and PNP. Only difference is that there should be an arrow mark. If the arrow mark is pointing outside, then it is called as NPN transistor. Then if the arrow mark is pointing inwards, then we call it as PNP transistor. Okay. Now let's go to the circuit diagram. Okay. Now in this experiment we are actually using NPN transistor and in CE mode. Okay. So therefore the circuit diagram looks like this. So let's consider we have a transistor here. So this is NPN transistor. So this is base, and this is emitter, and this is collector. So it's, when we go back to this is base is positive, that is p type, this is n type, and this is n type, collector is n type. So if I connect a battery here, okay, so one second, let me click this, okay. Now this is a variable battery, okay. Now the positive of the battery is connected to the p type, and negative is connected to n type n. So similarly here, okay, this is VBB and this is VCC, okay. Therefore this emitter base region we call it as input circuit, where the positive of the battery is connected to p type Pn and negative is connected to Nn. Therefore this is forward bias. So similarly here, this is output. In the output, the n type or n end is connected to the positive battery and p end is connected to negative. Therefore this is called as a reverse bias, okay. So let's come back to the circuit diagram, okay. So we have a battery source, okay, which is variable source, okay. Since it is a common emitter, so emitter is common. Now here and resistance is connected and followed by a micro ammeter, okay. Across this terminal voltmeter is connected. Let's say this is RB and this is VBB and this is VBE actually, and this is current through this is called as IB, okay. Now this is positive and negative, positive, negative. So the positive of the battery is connected to its base and negative is connected to the emitter. So this is forward bias and this is input circuit, okay. Now here a milliammeter is connected and a variable source. This is VCC, this is voltmeter, say VCE. Okay. So this is output circuit. So the aim of the experiment itself says to draw the input and output characteristics of an NPN transistor in CE configuration and to determine its current gain and input resistance. Now when we perform this experiment, what we will do, so it will be like this. In the input characteristics, so we keep VCE is 2 volts, the output is 2 volts as a constant, and we will vary the base current from 10 to 100 in steps of 10. Then correspondingly we will measure what is the voltage across base emitter, that is VBE. There is one more case also. You can actually vary the voltage from 0 to 2 volt and you can correspondingly measure IB also. There is one more method also, but here in this case we will consider varying IB in steps of 10 to 100 in steps of 10, and we will correspondingly we will measure VB. So this is feasible, therefore we are following this method, okay. Whereas in the output characteristics we will keep the base current is constant, let's say for example 25 microampere, then correspondingly we will vary the VC voltage and we will measure the collector current. We will vary from 0 to 2 volts, say 0 to 1 or 2 volts and steps of 0.1, then correspondingly we will measure the IC. Similarly, next value will be IB will be 50 microampere, then we will vary VC from 0 to 1 volts, then correspondingly we will measure IC, okay. So when we plot the input curve, the input curve should be looks like this. This is the expected graph, okay. So if it is input, so it is IB is plotted along y axis and VBE is plotted along x axis. VB is in volts, IB is in micro ampere. Okay. So what happens initially? So for a fixed VC, say for example 2 volts, this is constant. Okay. So initially with increasing voltage, so current will not be increased much. So after particular voltage only, what happens? Current starts increasing. Once crossing particular voltage, then linearly the current increases. The curve should look like this. Okay. Whereas the output curve should be like this. In the output characteristics, so we will plot IC along y axis. IC is milliampere, and this is x axis will be VCE in volts. Okay. Now what happens with increasing the voltage, the collector current increases linearly. Okay, and after reaching particular voltage, and it becomes constant, saturated. So I say this is for IB1. Okay. Suppose if I repeat the output characteristics for other particular value of IB2, let's say for example IB2, where IB2 is greater than IB1, then the curve should look like this. Now what we have to calculate in this, so we want to calculate what is input resistance and also current gain. So how do we calculate the input resistance? The input resistance should be calculated from the input characteristic curve. This is input characteristic curve. Now from the input characteristic curve, what we will do, so we will extrapolate this linear portion of the curve, extrapolate to the x-axis. Therefore it will meet at particular value on the voltage axis. Okay. So this value we call it as knee voltage. So this is a forward voltage, after which the current in the PN junction or transistor increases linearly with increasing the voltage. Now for this we take a slope, say for example this is delta IB and this is delta VB. Okay. So according to Ohm's law, we make use of Ohm's law for the linear portion here. So input resistance will be equal to delta VB divided by delta IB. Sorry, it's VBE. Okay. So the slope of this curve and you take inverse, so you will get the input resistance. Now when we come to the gain, how to calculate gain? Now since it is saturated here, so extrapolate to the y-axis, and also extrapolate to the y-axis this one. Okay. This curve is for IB2 and this is for IB1. So correspondingly we will get here IC1 and here IC2. So therefore the current gain we call it as beta, which will be equal to delta IC2 minus delta IC1 divided by delta IB2 minus delta IB1. So basically gain is equal to output current divided by input current. So here output current is the collector current, therefore it's a difference between the IC2 and IC1, and input is base current, that is difference between these two. Okay. So therefore once we calculate this beta current gain, this we call it as current gain in CE configuration. So using this value we also calculate alpha. Alpha is also current gain, but it is in common base configuration, CB configuration, which will be equal to beta divided by 1 plus beta. So basically, so it is derived, it is delta IC divided by delta IE. Okay. So it is output current divided by input current in IB configuration. In IB configuration, then input current will be IE. Okay. Okay. Now let's go ahead with the experiment. So when you perform this experiment, so you will have a kit like this, okay, so on which circuit diagram is written. So referring to the same diagram, we have a VBB, okay, we have a resistor, we have a VBE, voltage across base emitter terminal, we have a micrometer. This is a region where we connect the transistor, and we have milliampere, milliammeter, voltmeter here, VCE, and this is a VCC, okay, this is a common emitter, okay. So you will be provided with this kind of box where you will have a transistor. So when this is a transistor. So if you carefully observe, there is a notch here, okay, there is a notch, okay. The terminal which is near to the notch is the emitter, next base, collector, okay. So we will connect this here. So transistor is connected. Now let's connect first input circuit. So I will connect the source first. So source is connected, okay. Now input, the RB input resistance is already there, okay. Let's connect this micrometer. So micrometer, if you want to read, this is a micrometer and the values can be read from this, okay. So it's a digital. So positive of the micrometer is connected to positive, and negative of the micrometer is connected to negative, and we have voltmeter. So positive of the voltmeter is connected to positive here, okay. Negative is connected to negative. So here this terminal is common, since it is common emitter. So doesn't mean whether I can connect here or I connect here or connect here, it is same, okay. Therefore I will connect it here, okay. So it's a common emitter. So better, okay. So then, so input is done. Next let's connect output. So output, this is the source, source is established, and the milliammeter positive is connected to positive, milliammeter negative is connected to negative. So there is VCE, voltage across emitter collector terminal. So this terminal is common when we are using input. So this voltmeter is common, therefore we will connect it here when we are using input. When we are doing output characteristics, this is taken out and this will be connected here, therefore this is a common, okay, common voltmeter we have. Now let us start our experiment. So make sure all the knobs should read 0, okay. Now the tabular column itself says in the input characteristics, you should keep VCE is equal to 2 volts. So it means this should be 2 volts. So now I have connected across this output VCE, and I will vary VCE and keep it 2 volts. So you can use, this is a fine and this is a coarse adjustment. So this VCE should be constant throughout input experimenting, okay, or throughout studying input characteristics. So I'll remove this, okay. So even if I remove, it means the output, that is VCE voltage, should be 2 volts only, it will be 2, okay. Even if I remove this, it will be 2 only, okay. So now we will study the input. I'll connect it to the VB now. Now the table of column says vary base current from 10 to 100 in steps of 10 and correspondingly measure voltage across base emitter VBE. Okay. Now, so since I am studying input characteristics, so I don't have any job with this. Now I will use this, okay, in order to vary the IBE. So IBE is the base current. It is in the units of microammeter. Okay, microammeter. So microampere in terms of we'll measure. So we'll vary this. Let's keep 10 now. Okay. So for 10, what is the corresponding voltage? So now look at this, the voltmeter is connected across these two terminals, so it means we are measuring VBE. So VBE is 0.60. So here IB is 10, VBE is 0.60. Next value will be 20. So for 20 it will be 0.63. Next 30. It's 0.65. Next 40, 0.67. Next 50, 0.68. Let's see for 60, 0.70. 70, it's 0.71. 80, 0.73. 90 microampere, it is 0.74. And 100. So input characteristic experiment is done now. Now let's move on to the output characteristic. For doing output, again the tabular column says that keep IV base current is 25 microampere, then vary VCE and correspondingly measure IC. So to do, first you bring this back to the 0. Okay. Now disconnect this VBE and connect VCE. So it means now I have connected this voltmeter. So let's keep first IB is 20 microampere. So IB is this. So let's keep 25. So before doing, so you can even make it 0 here. Okay. So let's keep 25. Okay. So this 25 should be constant throughout this part of the experiment. Okay. Now VCE should be varied from 0 to 1 in steps of 0.1. Okay. So let's vary VCE. VCE for 0 it will be 0 only. Okay. This is IC, because IC is here, so IC is connected here. So for 0 it will be 0. Next for 0.1, now I am going to vary VCE. 0.1 it will be 1, 0 1 no decimal, it is 1 only. Next 0.2, it is 3. Next 0.3, okay, it is 3 only. Next 0.4, .3 only. So after increasing Further, so it will be 3 only. So for all values it will be 3, 3, 3, even up to 1, 3 only. Okay. So next, bring it back to 0, vary IB to 50 or keep IB as 50 microampere. Now this, throughout this part of the experiment, again this IB is constant, that is 50 microampere. Now again vary this VCE from 0 to 1 in steps of 0.1. And correspondingly measure IC. Now let's keep 0.1. Okay. So 0.1 it is 3. For 0 it is 0, 0.1 it is 3. Next 0.2 it will be 7. It is 7. Further increasing voltage, so no variation in the current, so it means it is 7 for all other voltages. Okay. Now what we should do here, so again we will plot the input characteristic curve and output characteristic curve. Exactly it looks like this. Okay. So when you look at this input value, the input value for IB, so you will start from 10, 20 like this, we plot. So you can consider scale of anything. Okay. So scale, if you want to consider, so you can consider along y axis 1 unit you can consider which is equal to 10 microampere, that can be considered, and along x axis 1 unit you can consider which is equal to 0.1 volts, that you can consider. But when you are doing this, start from 0, so it means up to 0.6, so no variation in the voltage, it will be this only. Okay. After 0.6 only there will be a variation only within the 0.8, so only within the region, so you will have a variation, so you will have a curve like this, and extrapolate to the x axis, you will get the new voltage, and take a slope of that curve, linear portion of the curve, and take inverse of that, so you will get, you can calculate the input resistance. Okay. Now when we come to the output, so same scale can be used. Okay. So scale in the sense, so along x axis you can consider 1 unit is equal to 0.1 volts, and along y axis, so it depends upon the value you can consider, either you can consider 1 unit is equal to 1 milliampere, or it's good to consider 0.5 milliampere, even less than that also is fine. So depends upon the value we can consider. So if you plot, so for a particular value, let's say this is IB1, so this is IB1 for 25 microampere. So let's say this is a curve you will get, let's say this is 25 microampere. Okay. And IB2 is 50 microampere. Okay. And this is a curve you will get like this, and extrapolate to the y axis correspondingly, you will get IC1 and IC2. Then you substitute in the formula, beta is equal to IC2 minus, so let's say this IC2 minus IC1 divided by IB2 minus IB1. Okay. So this will give you the beta value. So once you calculate beta, substitute back in the formula, alpha is equal to beta by 1 plus beta, you can calculate the alpha. So this is current gain in CE configuration. So alpha is also current gain in CB configuration. The values you should get in this experiment, so you will get input resistance is around 1500 to 2000 ohms, okay, approximately, and beta value you will get around 50 to 250, and alpha value approximately will get 1. Okay. So by looking at this value, the beta and alpha, these are the current gains, this is in CB and this is in CE mode. So we can say that this NPN transistor can be used as amplifier only in CE mode, because we have a gain is more, amplification can be possible in CE mode, not in CB mode. So CB mode it is only approximately 1, therefore, so we can use in CE mode for a amplification applications. Okay. Thank you.